everyone. Welcome to the 4C Conference webinar series. Today we have Ty Smith of CEMTEK. Ty has been with CEMTEK and this industry for quite some time and is a recognized expert in the subject matter. And with that, I'll turn it over to you, Ty.
Thanks very much, Steve. So welcome everybody. A couple of people that was spoken to ahead of us starting gave us an idea of what they want to hear. I'm going to go over tunable diode lasers, mostly for, in this instance, for PS-18 NH3 compliance monitoring. But I will touch on some other stuff that we're doing as far as the other gases and some of the applications and trials that we've been a part of and the successes that we've had, and then some things to look for the future. So welcome, appreciate you all taking the time to come and watch this, and hopefully we can share all the information that you're looking for. If you have any questions, please, reach out to me afterwards, send me an email, you want to send a phone call, and we'll be happy to give you any more information or further explanation of what we discussed today or anything related to this. Okay, so what we're going to go is a typical method for monitoring NH3, which would be differential, either with an analyzer or inlet-outlet monitoring, the Tunable Diode Laser Spectroscopy technology, the EPA rule PPS-001 or PPS-01 as people call it, and the performance spec 18, which was originally written for HCl and is now actually going to be used for a host of other gases, or other gases that are not covered under the Clean Air Act or other regs. Certification and testing, factory interference test, and then a demonstration and some installations that we've done for various applications. So this is what your typical methods for monitoring ammonia looks like. So you either have an inlet-outlet mass balance method where you're measuring the inlet NOx and the outlet NOx, your ammonia consumption, ammonia ejection rates, and then calculating your ammonia slip based on that. Or you have a differential NOx, which requires an additional analyzer and converter on the stack, requires additional CEMS and a converter and higher additional cost. Similar to the cost of a laser install, but the long-term maintenance cost is where the real savings are. This is what that install looks like. You have a ammonia converter up on the stack where you extract the sample through the probe. It splits. Part of the sample goes down to your regular stack analyzers, and another part of the sample goes down through a very high temperature stainless steel converter that converts the ammonia to NO. And then from there, it after converts the ammonia to NO, that goes down to a secondary NOx analyzer. But first has to go through a chiller for moisture knockout and particulates, control the flow rate, the pressure, the back pressure, and then over to the additional NOx analyzer. So you need heated tubes, additional heated tubes in the umbilical, and an ammonia converter, which the lifespan depends on how much ammonia you slip. If it's a new installation, new turbine, new SCR, those converters can get used up very quickly as they're fine-tuning the system. And then after that, they get replaced every few years, and they're going to be tested regularly to make sure that you're getting the NH3 to NO conversion. You also need extra electronic components, extra I/O on the data logger, and the PLC, and then some control and functionality added there. So pumps, seductors, filters, that sort of thing, and the additional NOx analyzer that needs to be maintained and have spare parts, etc. Okay, so sorry about that. In this presentation, I have Gary, who put this presentation together, speaking over me on some of them, so I apologize for that. So PPS-01 is an outdated, sort of from a technology standpoint, according to EPA's website, and they highly encourage people to use Performance Spec 18, Appendix F Procedure 6 for for monitoring ammonia. And that was written for HCL and CEMTEK and Unisearch, who makes this analyzer for us and for many other applications. What they did was we used one of their analyzers to do the demo to EPA for HCL, and then the ratio rule was written for PS-18 to cover FTIRs, extractive laser, which CEMTEK also sold, the AP2E, and then the cross-stack tunable diode laser from Unisearch, which the US reps for in these PS-18 applications. So the rule was not, I would say, written around this particular instrument, but it was written around cross-stack integrated path laser monitoring for HCL, which is we're now using that same reg for ammonia. So this is just a very basic installation of a TDL. If you look at the bottom picture there, you can see the little gray optics box on either side of the duct. That's after the SCR. In this application, yeah, we're measuring NH3, but you see there we can measure HCl, H2S, H2HF, and methane, hydrogen cyanide, CO2, CO2, and a few other gases as well. And we just completed some demos with those gases very successfully. Typical installation for a single setup would be, like you saw in the previous one, optics up on the stack, gain out to controller that can be, up to 2,000 meters away, or even further if need be. But we're not going to need that on any of the power applications or refinery applications that we do. Glass, cement, steel, other, waste incineration. So what is a TDL? So there's a very small laser, which is a telecom laser, very long life. We say 20, 25 years, but in reality, we haven't had any lasers fail. And we've been doing these for about 16 years now, and we haven't had any lasers fail on us yet. So there's really no spare parts to keep for this. The laser emits a specific wavelength. You order the wavelength that you need, and then you control the temperature and the current to get a very fine line of the spectrum that you're looking for that particular gas, whether it be NH3, HCl, CO, CO2, whichever one you're looking at. So it's a very fast response time, excellent sensitivity, independent from radiation from other sources, optical effects and edalons that may mess with the background. System doesn't require calibration. And I know most of you probably heard before, somebody wants to sell a new analyzer and says you never have to calibrate it. In this instance, we've got some of these out there for ammonia now for 15 years, and we've never had to adjust them. We've never had to go in and say, okay, we're putting gas through, the gas is 25 ppm, we're reading 20, and we've got to adjust it up to 25. If we're not reading the gas, then there's something wrong with the instrument, which even that rarely happens. So we have gas that we can flow through them to test them and make sure, and we can pass daily calibrations in a couple of different ways, which I'll get to. But it really doesn't need to be calibrated. They just don't drift. Relatively inexpensive, wide dynamic range, and can easily correct for real-time swings in power, heavy dust laden environments, moisture, things like that. And the way you do that is you set the temperature and the power to exact wavelength you want. Then you change the power slightly, that wavelength changes slightly, and you'll see the dirt, the dust, the moisture, dirt on the optics. And then you go back on the wavelength you're looking for, and the additional light that you lose at that point, that has to be the target gas you're looking at, because you're back on peak. And you know that we lost a little bit of light, but more than we did with power, with the dust, the dirt, and the moisture. So that has to be the target gas we're looking at. And then based on that amount of light, we can determine the concentration of the gas. This is just the range that we work in, so you can near visible and UV, near UV, and we're doing various different technologies across that with the Tunable Diode Laser and the DOAS. And we've got some work that we're doing with QCLs as well, but not for cross-stack at the moment. I take that back, except in one instance where we're not cross-stack, but we're doing extractive QCL for H2SO4 and SO3. And then we've got a trial coming up with the DOAS pretty soon to use the DOAS to look for H2SO4 across some coal-fired stacks. That test is coming up in the middle of August. Here's a different installation application, optics on the platform, the controller's down on the ground. Nothing to really maintain up there. There's a lens that gets cleaned, and we'll show you that later. Here's the controller in the shelter. You can see the data on the screen down there. In addition to that, you can have a laptop where you can bring up all the configuration data for that instrument and that application on the laptop. It can give us remote support. We can dial in and diagnose the system if there's an issue with it, which again also rarely happens. So it's very convenient. That doesn't have to be up on the stack. That's down on the ground. There's the launcher and the optics reflector. This here is an internal reference cell. So one of the ways that you know that the instrument's working and is on the target gas that you want, you have a sealed cell, which you can see there on the left with a known concentration of gas inside there. And a small portion of the light, about 10% of the laser light, splits off and goes through that cell to a separate detector. And it references against that gas on every measurement so that we know that it's measuring correctly. So it's another way that we check it. We have applications where we use that for our daily calibration. So we select one of those spot checks, let's say at 7 a.m. every morning, and that becomes our span calibration. A couple of ways you can do this, depending on the size of the duct or the size of the stack. You can do a single pass across the stack. And we'll cover this, but as you can see, we broaden the beam as it goes across so we can flood the port and the detector with light. So if you get some movement and twisting from temperature, we can still hit that detector on the other side. And we can make that beam even broader if needed, or sharpen it, whichever way we want. So that we just adjust that on the launcher side. You got a fiber optic with the laser light going up. And typically we don't have anything else up in the box except that, unless we have a very long coax coming back, then we'll have a signal booster on the receiver side just to boost that coax signal going down to the detector. We can also do that with fiber optic, let the light come back down fiber optically to the analyzer if need be. Usually when we do that, we'll install both. We'll install the coax cable and the fiber optic, and have them both there, that if there's ever an issue with the detector, you can switch over to the coax cable as a test. And then we also put multiple core fiber optics up there so that if there's an issue and you suspect that it might be the cable, you can go ahead and switch fiber optic connectors. There's the dual pass. You go across the stack, you hit a detector, sorry, a reflector, and you come back and hit the detector. We can do multiple points up to 8. So we can have fiber optic cable gain up to 1 set of optics, and then you have a beam splitter and a multiplexer. And then the multiplex will, let's say, do 20 seconds across the one fiber optic and 20 seconds across the other one. And then you can get measurements on 2 different applications. Sorry, my daughter's cat came in the room. Yeah. So there you see we can broaden the beams. Even if we get some changes in the alignment, we still hit the detector on the other side. And we've had some applications where we really thought it would be tough to make this work. And we were able to solve that by broadening the beam, and it worked extremely well. That's the lens cap up on the stack. Usually that's all the maintenance you need. There's no pumps, there's no chiller, there's no heated converter, there's no sample transport. You take that cap off, you wipe it off on the inside. That area is purged with clean, dry instrument air or a blower motor, depending on the pressure we're dealing with. You wipe that cap off on the inside. If over time that cap's got a coating on it, it gets scratched up, it's still going to work correctly. But there's 4 screws holding that lens in. You can take that lens out and keep it as a spare one and just replace that if it gets scratched up from cleaning. On the right side there, you'll see the fiber optic coming in, and then the little knurled knobs that you use for adjusting the alignment. Here's some testing that FERCO did, Fossil Energy Research Company in California. We work closely with them where they tune an SCR, and then they use this analyzer to give them feedback. And just on a single turbine, the reagent savings for the year, this is very conservative. We had customers tell us that they've saved way more than this, way more than the $42,000, because they were over-injecting a lot. This is one that was running pretty good, and they still saved $42,000 in reagents. So potential savings are really big if you don't have proper control of your ammonia slip and your ammonia injection. So meeting TDL compliance, PPS-01 versus PS-18. Here's the checklist against it. So on the left side, you see PS-18. We do a factor interference and level of detection test, field LOD determination, 7-day Cal drift test, and we do some spike testing. So on PS-18 for HCl, we were looking at very low parts per billion, 12, 15, 20 parts per billion, and we were able to do that very successfully, even just bleeding in some cal gas and mixing it with in the port, mixing it with a stack gas. We were still able to see those very low LODs on the HCl, and it's the same with ammonia. Many ways that we can test this and prove it out, but PS-18 is very specific. If you compare that on the right side for PPS-01, and that's why the EPA is not recommending it anymore, because the technology is outdated. There's no factory interference and LOD test, no field LOD test, no 7-day drift test, no Cal Audit linearity. With some of them have it with mistraceable gas, but it's not in the regs. The light attenuation test isn't there. We have that in PS-18. Both have a radar, and temperature and pressure verification test we do, and then validation audit spikes on PPA, but we do some of that on PS-18 as well. So it's a way, in my opinion, and many others, it's a way better regulation, because you really are getting an accurate instrument. When we're all said and done, it's certified to a much higher standard than PPS-01. There's a close-up of that sealed cell with a known concentration of sealed ammonia in there that doesn't degrade. Those stay good for a long time, and it reference up against that. This is what that setup looks like. You got the beam splitter. Part of it goes through the reference cell, and the other part goes up through the stack. On the left side there is our flow-through cell. So for ammonia, HCl, and a few other gases, we have a flow-through gas cell in the analyzer down on the ground, let's say, 100 feet away from, 200, 500 feet away from the stack optics, have a bottle of ammonia or HCl or other gas, and you flow it through that cell, and the light from the laser goes through that cell, out the other side, into the fiber optic, and then up to the stack and across the stack. So we can introduce the cal gas into that path. We take a reading of the stack gas before we do this. We flow the gas through. You get a very quick response because it's down on the ground. The gas is very close to the analyzer. You don't need to flow gas up to the stack. It flows through that cell. And then we use a higher concentration of HCl or ammonia gas, and then we correct that to the path length across the stack. So we can get a very accurate representation and get down to some very low numbers where it would be difficult to get a cal gas concentration down that low certified from a vendor. It's easy for us to do that with these flow-through cells. At any time, if there's a question about the system, its accuracy, if you have a system and you see no ammonia slip and you wonder if the instrument's working, flow a little bit of cal gas into this, it'll see the ammonia, it'll go through that fiber optic up to the stack, across the stack, down back to the instruments, and you'll know that you're seeing the ammonia. Another simple thing you can do is up on the stack, take a bottle of Windex up there, spray it into the port, and you'll see that ammonia as well. So, and then you can also flow zero gas into this flow-through cell, so we can do a zero check, and then we just subtract out the background. In addition to that, we do pressure and temperature correction for the gas in that cell and for the stack temperature, so we can correct that. So we get these down. It's taken years of of research and trial and error, and really Unisearch people, the folks there have done a phenomenal job getting this instrument to where it is. Absolutely excellent results that we're seeing. This is what that looks like with the flow-through cell. Down at the bottom, it goes through the audit cell. And then you also have the reference cell up at the top. So you're checking this two different ways every single time it takes a measurement. You can have a multiplexer where you can go through to the flow-through cell and bypass the flow-through cell as well if you want to. If you don't want the signal to go through the flow-through cell, have a multiplexer bypass that, and then you only add the flow-through cell in when you're flowing gas. This is a very conservative summary of comparison for NH3 TDL. I actually need to have Gary update this. I don't think it's accurate at all because the spare parts on this are very little. There's really not much that we do on these. But you still see there's a significant cost savings over traditional gas analyzers when measuring ammonia stuff, but it's even more significant than that, and we'll get that corrected. So here's a particular, the one that we're talking about, where we did an application for PS-18 monitoring at a specific plant, and they were very generous to allow us to share that information. Pacific Corp Bridger plant in Wyoming. This was the first one that was done for NH3 compliance in the country using PS-18, and CEMTEK did that. How this worked is we supplied an analyzer because they weren't happy with the current technology that they had. We supplied an analyzer as a demo first to prove that we could do it. We pretty much knew that within an hour or so of putting it on that we had good data. Typically, once you get this installed and you switch it on, you have data within 2 or 3 minutes very quickly, and you know right away that it's working. So they immediately saw the benefits of the system in their ammonia injection control. No maintenance, didn't have to touch it, put it up there, it just worked. There were some issues in the configuration. They called us, they gave us remote access. We got the PhD on the line. He logged in, he looked at the data, solved the problems for them, and we were up and running. And that was just sort of fine tuning as you get this set up for a particular application. And since then, the things run just beautifully. And we're now just quoted them our second unit, and we believe there's more coming where we're going to certify them for PS-18 compliance. And we've got several other facilities that we have quotes out to right now that we expect to be doing theirs very soon as well. We use the Model 7000. This has been since actually somewhere early 80s this was developed. It's been used in a ton of applications for safety, for HF monitoring at aluminum smelters, for open path monitoring in different applications. So as I discussed earlier, we did the trial. Trial was very successful. That turned to an order. We did pre-testing at the factory. So when one of these gets ordered, we set it up at the factory for that particular path length. We calibrate it, we put the gas through it, we do a full factory checkout on it. We add the solenoid valves for calibration gas, a data logger to go with it to collect the data, to do calibrations, averaging, all of that stuff. It goes with our KVB-Enertec software, and then this gets installed on the site and we certify it. Once it was done, they hired a RADA team, we went to did the RADA test, and then we sent one of our field engineers out there to do all the field testing. So the optics are located inside the stack annulus. It's a wet stack with high moisture. As you can see, those of us in the industry know that's just moisture coming out of the stack. It's pretty clean. But even with a cold winter's day where sometimes that'll condense down inside the stack, where you'll see more moisture, we haven't had any issues with our signal getting across, even though moisture droplets are present. Low stack temperature, 125 to 200, and typical ammonia levels are really low. Mostly we see them running, 1 ppm or less most of the time. That's what the optics look like up on the stack. very, excuse me, very basic. In this instance, we don't even have the booster there. It's just the receiver fiber optics going, coax cable going down to the controller downstairs. That's all you have. You have one of these on each side of the stack. No pumps, no filters, no heated lines, nothing. Low cost, low maintenance. The only thing you're going to do there is clean that lens if it gets dirty. If you've got a negative pressure stack, that lens will stay clean for a very long time. Even if it gets dirty, it's still going to work pretty good. The way these work is if we can get 10% of the light that we send across, even losing 90% of that light to dirt on the optics, moisture in the stack, dust, whatever, and 10% hits the detector, we can still make a very accurate measurement with that 10% of light that gets through. So it makes it very versatile, and it's not like, you know, you get a little bit of dirt on the optics and you're dead in the water. Not at all. In the trial that we were doing, where we're up on a stack matched up against a CEMS that's installed that we supplied years ago, and we're measuring CO, CO2, NH3, and O2 with the TDL, and we're measuring NO, NO2, NH3, and SO2 with the UV DOAS. There was moisture that had accumulated on the optics from a very cold day, because this was just a trial at temporary setup. Even though the lens was almost completely fogged up, we were still passing daily calibrations, and they were doing a radar, and we were passing the radar. But I noticed that into the second run, between the second and the third run of the radar, I took that lens cap off, wiped it down, put it back on. It took all of 2 minutes at the most, and the numbers came back exactly the same, and it ran. So that was the only maintenance we'd done on the unit, was cleaning the optics a couple times, because these were supplied outdoors through the winter, and we didn't expect them for it to be that long, so we didn't have heated optics and heated flange, which on a permanent installation outdoors in winter, especially in the northern part of the country, you would absolutely have that, and you wouldn't have that fogging issue. And that's just because the port we were on stuck out about almost 3 feet, and the cold air was hitting the port, and the gas was condensing inside that port. So we insulated the port, we added a heater to the box, and that resolved the problem, and we haven't touched it. That's the shelter on the ground. It's 400 feet away, and the analyzer's in that shelter. There it is, showing the moisture content and the ammonia. So just a comparison of the existing instrument and our data. So you can see the CEMS is in blue, numbers a little bit more unstable, jumping around, responds a little slower than ours. If you look at the red line with the TDL, you can see it responds quicker. There in the middle, it goes up quicker, it goes down quicker, and it gives you a more stable reading. So excellent performance, outperformed what they had, and it was an easy decision for them to buy it. Montrose came out and did the testing to compare up against ours. We've done this in various applications where they've done wet chemistry, they've done hot FTIRs, grab bag samples, various things to compare up against ours, and it passes the radar every time. So PS-18 certification requirements, it's a factory control test that was done, directed by John Pisano from Unisearch. And then interference test, we had to develop all of these tests for PS-18 when we did our first trial for HCL. So CEMTEK, like I said, a lot of this is written into the PS-18 reg. It's because we did that work with the EPA on trials and at their facility to develop these interference tests. They challenged us to do certain things that we weren't doing at the time. Went back with Unisearch, figured them out, and were able to get the tests and done and exceeded their expectations and worked very well. So we do temperature verification, the light attenuation test, pressure check, response time of the instrument, the field LOD level, and we can spike the gas into the port to see, or into the flow-through cell to make sure that we get in that, that low LOD. 7-day drift test, no problem at all with flowing cal gas and with the sealed cell. We can do low, mid, and high. There's an additional way that we can do low, mid, and high if we're not using calibration gas, is the sealed cell we have in the instrument. We can have additional sealed cells that are external in a little handheld module, and you just hook up the fiber optic to that in and out and add that to the light path. And you can have 3 different levels of sealed cells, and you can do your linearity check that way. Or we can do it with this traceable gas, and then the radar test as well to prove that it's accurate. And the results have been absolutely great so far. Factory interference tests, you have to flow other gases that you know are possibly in that stream, moisture, SO2, NO, NO2, CH4, whatever else is in there, and you have to prove that it's not going to interfere with the gas that you're looking at. And we can achieve that by that very fine tuning of the laser power and temperature and keeping it tightly controlled. So he has the advantage of having the laser down on the ground or in a climate controlled environment with an air conditioning, where that laser is at a very specific temperature and the flow through cell is at a very controlled temperature. Some of the other TDL manufacturers, they have their laser up on the stack in the optics box on the stack on the port, and when the sun shines on it, they can get overheated or the temperature goes up, and that can affect your reading. Ours, that's not the way at all. You put that controller in a control room, in a shelter, anywhere. You need it in a climate controlled area. You flow the gas there. Your laser's kept at a constant temperature. So we have no problem meeting the performance of PS-18 because our temperature is controlled so tightly. And you just put it in an air-conditioned room. Doesn't have to be even, very tightly controlled. We don't have the sun beating down on it. If there's an issue with the instrument, you're looking at it down on the ground in the control room. And we can support it remotely as well. So we recently seen where another instrument was up on the stack and they had to put some shields on it because the sun was beating down on it on the TDL. We just don't have that issue at all. And then because we're fiber optically coupled, as I said earlier, we can have, if you're not doing this for compliance and you want to measure ammonia slip at the duct and you've got 2 turbines side by side or 2 units side by side, we can split the fiber optics, send it out to each one with 1 instrument, and you can lower your overall cost. And we can do up to 8 instruments. It slows your response time down when you do 8, where we got many where we're doing 4 and 6 that we've been operating for 15 years very successfully, almost no downtime at all. Just clean the lenses quarterly. Somebody goes there and cleans the optics. That's it. We take care of the thermal effects based on temperature because we have the flow through cell at a controlled temperature. So, and then we're measuring the stack gas and we're correcting the calibration gas for the temperature, the path length across the stack, and correcting the cal gas and the response to temperature and pressure and path length. Moisture levels, whatever moisture can be certified, it's very accurate. And we've done interference tests. We say 450 and 700. I think we've done them now up to about 1200 F. Recently completed some testing for a customer. They're using, and that was, it's the same laser that was on the CO and O2, where they're measuring CO and O2 across the duct at the turbine exit so that they can turn down their turbine and run it at a very low load and still stay in compliance and keep it running warm for when they start up again. So they're using our accurate O2 and CO across the stack to give them the control they need, and it's working extremely well. So linearity over the range is measured. These systems are inherently linear anyway, but we have to prove that out, and we do that through the cal gas or the sealed cells, and then through spiking as well. You can spike that gas on either ports on side of the stack or in the flow-through cell, and it ends up being very linear. We can see that when we do an interference check as well. We do an interference check at various levels, and there's no interference, and the analyzer is very linear. This was a test setup We just recently did this at our factory in California. There in the top picture, that's a heated cell up there, so we can vary the temperature like you would in a stack, and we can go all the way down from ambient up to 1200 F. Now we've tested it, and what effect that has on the gas, and then we can build curves for specific applications, and correct for any differences there. It's a dual pass setup using the zero unit search TDL. And then we use a hovercal to introduce known concentrations of moisture, and we've really ramped that moisture up, I believe, up to about 50% now, and still not had any issues in that cell in our testing. We can use certified gases or uncertified gases for testing, and we hit the gases every time. That's what that test cell looks like. It's much like what you would see up on a stack. It's the same thing. We're just flowing the gas through a cell. Here's the linearity test. You can see the points that we hit on there. It's extremely linear because you're always correcting for any changes in temperature and pressure on that flow-through cell that you saw that we have in the lab. The pressure really doesn't change there. So, and up on the stack, if you have minor pressure changes, it's not even an issue. We don't have to correct for it. If you have large pressure changes, then we will add that in and correct for it. We definitely want to feed the temperature of the process in, so that if you have this on a turbine, you have this on a coal-fired duct or a waste incinerator or some other plant, glass manufacturing, steel, we've got them in a bunch of different applications. If the process shuts down, we're measuring that temperature. We're also bringing that signal that says the process is shut down. So at that point, if the ammonia number changes, we're watching out for that, and we can say, okay, the process is down, you can ignore the number. But typically, even if you've over-injected your ammonia and saturated the SCR, and you shut down, and as you shut down, it's off-gassing that ammonia still, we're going to see that as it slips by, and we're going to measure it all the way down. We're doing a direct absorption analysis, and which makes it very accurate. We go the extra, Unisearch goes the extra mile on the analysis to make sure that the data is correct and correcting for the temperature changes that they might encounter. As you can see there down at the bottom, extremely linear from 0 to 480 ppm. We have tests where we have this on the stack alongside a differential NOx with an ammonia converter, and we match up their number right on the money. The customer wanted both systems installed because they got a very, very strict ammonia slip limit. If they go over 5 ppm, they have to shut down, so they wanted a backup of the two systems. Their differential NOx has been down multiple times. Our laser hasn't been down once. So they still use both. They just want to be sure. But that's been about 7 years now, and they have almost no downtime on that laser because there's just no components to fail. And they just clean the optics when the unit's down, so it's always running, giving them data. Bunch of stuff to do, but there's just the interference testing that we do, and the different levels of gas that we put in. And this is all for PS-18 at one temperature. So we do a bunch of testing on these instruments. It's not simply, grab an instrument, flow gas through it, passes cal, ship it out to site. It goes through a bunch of testing ahead of time. The good thing is, once we've done this for a customer and they want to buy a second one, we don't have to do all of these tests again for that customer, as long as the application's similar or the same. There's some stuff that we've already taken care of. But the on-site testing's always got to be done. You've seen similar pictures to this earlier, but this just shows the setup where we have the cal gas cylinders. They flow through that flow-through cell, which is inside the analyzer. The beam intensity test that we have to do to make sure that we're not losing any of the light. Temperature and pressure verification. So this, what we're going through, this is just all the paperwork that we have to do for PS-18 to make sure that this instrument's very accurate and giving you data that you can rely on and use to report and control your emissions. So control your ammonia injection, which ultimately helps control your emissions. So we've had multiple customers report that they have far better control of their process now with ammonia injection on their emissions, because when they get a slip number, they absolutely believe it. On coal-fired units, they tell us that the moisture reading that we get is very accurate. And when they see that moisture number going up, it means one of two things. Your optics are dirty, or you have a tube leak in your boiler. They go up, they clean the optics, the moisture is still high. They notify operations that, hey, you have a tube leak. And they say, no, we don't. They say, you've got one that's developed, the moisture's gone up. Keep that in mind. If you shut down, you need to go check those tubes. And they've been accurate every time. 7-day cal error test, much like you would on a regular CEMS. You can see the accuracy there is very good. And again, we're compensating for pressure and temperature. And as anybody knows, if you float ammonia gas, you want to use the right regulator, the right tubing. You don't want any of that cal gas sticking anywhere where you don't need it or losing any of it. And that's where we have an advantage. You don't have to flow the gas for ammonia or HCl up to the stack, because they're both sticky gases. You just flow it locally to the analyzer, and that really helps with your accuracy testing. Low, mid, and high linearity testing that we do for PS-18. Passed all of them, no problem. And then the additional field tests that we do, the beam intensity, temperature, pressure measurement, response time, the measurement error, calibration drift, and field audit standard additional response, and then some other testing that we do with the radar test, and then some spike and bump testing that we do as well. So end result, you get a certificate, not so much certificate, but you get a report from us that shows all the testing that was done, which far exceeds PPS-01, and you can really stand behind that data and have the confidence that it's accurate every time you get that number. It's an accurate number. So a little bit of a summary. It's the accurate choice for NH3 compliance. Whether you're measuring for compliance or you don't have to measure it for compliance yet, you just have a target that you need to meet. Keep in mind that if you have an instrument that cannot meet PS-18, or you're looking at buying one, and maybe the one that hasn't done PS-18 may have their laser up on the stack, not down on the ground. If the rule changes, the state changes the rule, something happens, and you now need to do PS-18 compliance, you better be sure that the one you have can do it. And we've had some success with that, where the customers have chosen our instrument, because even though they don't need to meet PS-18 right now, if it does come, they're going to be ready. They know that they've got something on the stack that has really was, used for EPA as a guide to write the rule for integrated path measurement, and then an instrument that's passed PS-18 in the past many times for HCl and now for NH3, and it's essentially the same instrument, exactly the same instrument, just with a different wavelength laser. So many years of experience behind doing this and getting it right. The rest of the stuff, I'm just going to go over some stuff here briefly, real quick. So we're talking about the DOAS, the UV DOAS. This one shows the laser. If you look on the right side there, the DOAS that we have, we measured, as I mentioned earlier, NO, NO2 for NOx, and SO2 and NH3. And we're testing it soon on a qualified unit for H2SO4. So where we're headed is what we have running on a stack right now, on a turbine stack. The customer has two stacks. They put our equipment on one stack. They put another laser company's equipment on a different stack. Ours showed up on a Wednesday at lunchtime. It was installed, started up Thursday morning, and within about 15 minutes of it being powered up, we had NO, NO2. There are no SO2 because of the gas turbine, but we were looking for it anyway. CO, CO2, O2, and NH3 within minutes. And we've been running there since August last year. matching up against the CEMS. We've essentially done about 3 radars now, passed all of them. We're measuring NH3 slip with the tunable diode laser and the DOAS, and we're getting accurate NH3 on both of them. Both of them passed the radar test, and we've sold multiple of these for compliance, where the customer had an infrared SO2 monitor on the stack in a harsh application. They were working on it weekly to keep it running. They put in our DOAS 5 years ago, and they've never touched it since. They forgot how to work on it. It's performed so well for them. So the future we see for CEMS is having one TDL on the stack for CO, CO2, and O2, or TDL for CO and CO2 and in situ O2, and then a UV DOAS for NO and NO2 or NO, NO2 and NH3 on the stack. And that'll be your CEMS. No pumps, no umbilicals, no nothing. We've sold and certified a bunch for Part 60, and Part 75, we have the EPA coming to look at our equipment on site in a couple of weeks, and they're interested in helping us, or not helping us. They're interested in modifying the rule and making it possible to use these to comply with Part 75 for CEMS, and that's where we're headed. So we're excited about them coming out and looking what can be done. Right now, we're passing daily cals. These were installed in, like I said, August last year. Some issues with temperature and fogging of the lens. We had to play with the temperature compensation a little bit, got that all figured out, but these were calibrated at the factory. At CEMTEK, we flowed CalGas through them, we did linearity tests, we put in the correction factors, and they've never changed since it was put in August. We've not once had to go in there and say, okay, we're not matching the CalGas, we need to change the correction factor. We've not had to do that once in all that time. So I have a lot of CEMS experience. We would have had to adjust those analyzers multiple times. There's been no maintenance other than wiping off the lenses a couple of times, and that was because of the cold weather. Other than that, and the only thing we did change was the UV lamp. It's got a lifespan. This was a demo unit that had been used in multiple other places before it went there. It had reached the end of its life. It was a 5-minute change out to put the new UV lamp, and we didn't even have to do anything. Just put the lamp in, turned it, powered back up, and within 30 seconds we had an accurate NOx reading that matched the CEMS. Didn't have to change anything. So I think I've come close to reaching the end of my time. Thank you all for listening to me talk about this. If you need any more information, we'd love to share it. This, to me, this is very exciting stuff. We use this around power plants, around refineries, for open air monitoring, open path, perimeter, and fence line for NH3, for CH4. So exciting technology. Thank you.
Okay, questions from the audience, attendees? Okay, one question I have, Ty. What's the primary applications in the refining, chemical, and oil and gas space?
So for obviously for NH3, it's NH3 slip for the control, either to meet compliance or for control. On the other gases, they use it on like the heaters for CO and O2 there. HCN in chemical process, where we're measuring for HCN production in ppb levels and percent levels. UV DOAS on some inlet and outlet applications for NO monitoring. So those are sort of primary ones now. And then on the pipeline, we're doing a trial coming up soon where we're measuring for methane leaks, open path on their facility. And there's a new one now where they're testing TDL inside pipelines to measure for H2S.
All right, beautiful. Thank you very much. With that, we'll conclude today's webinar, and recording will stop here in 2 seconds.